Hey everyone. Well, you've brought me back out of retirement. Today we're going to look at the Level 2 Mathematics and Statistics Probability Methods paper from 2022. So let's get into it. So question 1. In New Zealand, the average person uses a mean of 227 litres of water per day with a standard deviation of 16 litres. Assume that water consumption can be modelled by the normal distribution. Part A. Find the probability that a randomly chosen New Zealander uses between 227 and 247 litres in a day. Right, so here we're looking at a normal distribution question. Essentially, we want to find the probability that a randomly chosen New Zealander, so we'll call that X. Sorry, we better use lowercase x. Uses between 227 and 247, right? So our lower limit here is going to be 227, and our upper limit must therefore be 247. So we want to find the probability that this random New Zealander uses less than 247 but more than 227. So how do we do this using the normal distribution? Well, we're going to need to go to our calculator. Let's go to menu, to stat. We'll click F5 for distribution. We'll go to F1 for normal. And then what we'll do in this case is we want to find we'll click NCD or F2 since we want to find a probability. Our lower limit will be 227. Our upper limit will be 247. What's our standard deviation? It is 16, right? So our standard deviation is 16, and our mean is 227. So our mean is 227. If we click enter, that will give us our probability of 0.3944. Part B. If two New Zealanders are randomly chosen, what is the probability that they both use less than 210 litres per day? So here we're not just looking at one New Zealander, but two New Zealanders, right? So we're going to have two events. Essentially, we'll find the probability for one New Zealander being randomly chosen, because that's what our normal distribution is for. It's for one New Zealander. And then what we can do is we can multiply that by itself or square it in order to get the probability for two of those events occurring simultaneously, right? So what's the probability that one New Zealander uses less than 210 litres per day? So that's going to be, what's the probability that X is less than 210, right? So if we think about this for a normal distribution, right? So this is our normal distribution here. So we want to find out, so assume that our mean here is 227, and we've got this number 210 litres. We want to find out the probability that X is less than that. So that's going to be all of that probability under that curve there. So therefore, what's going to be our lower limit? Well, there doesn't exist one, so we're going to put in the calculator negative 99999 ... And what's our upper limit going to be? Well, our upper limit therefore must be 210, right? Because that's the largest number that we actually care about. Okay, so how do we do this? Well, we go to similar to before, we'll go distribution, normal, choose NCD. Here our lower limit, well, it's negative 9999999. Our upper limit is 210. We've got the same standard deviation and mean, so if we click enter, that gives us a probability of 0.144, but we want the probability for two New Zealanders, right? So this is the probability for one New Zealander, but the probability for two New Zealanders, because since they're independent events, how do we find the probability of two independent events occurring simultaneously or occurring together? We have to multiply that. So we go 0.144 squared, or 0.144 times 0.144, and that should give us a probability of 0.0207. Okay, part 2. If the two New Zealanders were both chosen from an area that often experiences water shortages, how would you expect this to change your answer to part I above? So I guess the easiest way to do this is let's draw out two normal distributions. Okay, so the first one is the one that we currently have, right? So, okay, and we have a mean of 227, and our standard deviation is 16, right? So let's think about it this way now. So now we've got, so this is for kind of all of New Zealand, right? So now we're looking at something very specific, right? We're thinking of an area which has a water shortage. So if we have a water shortage, is our mean going to be 227? It's definitely not going to be 227, right? Our mean's going to be much less because we're able to get much less water, right? So our mean, for example, the mu or the mean might be like something like 100 liters, right? Where we have a shortage, so we can't get as much water, right? So therefore, right, if we take this and we think about it on, you know, this normal distribution here, 100 liters is going to be somewhere down here, right? But this is sort of, you know, a kind of new mean, right? So what I'm trying to get at is, look, if we choose 2 New Zealanders from, you know, say like, I don't know, Auckland was having a water shortage or something, right? That probability, so in part I, we have this probability of it being less than 210, it was 0.0207. But if we pick from somewhere where the mean is much lower, then 227 is going to be like all the way up here, you know, for example, on our normal distribution, right? So if this is 227 here, we'd be considering, you know, all the probability down here. Obviously, that probability is going to be much greater than this probability here. So what I'm trying to say is, both chosen from here, how would you expect this to change? We would expect that the probability that x, you know, is less than 210 would be much higher, since we have a larger or significantly larger area under the normal distribution. Okay, so we would expect, you know, our answer, you know, should be much higher. Therefore, answer or probability should be higher. Okay. All right, part C. Suzanne lives with her family of 3 children and her partner. She's conscious of water saving efforts, and she encourages her family to have short showers. Suzanne reads that the average shower time of New Zealanders is 8 minutes with a standard deviation of 2 minutes. So from the, you know, this is our theoretically here, we've got a mean time or an average shower time of 8 and a standard deviation of 2, and we're just double checking that they're both the same unit. They are, so that's not a problem there. So what does she do next? She times the showers taken by her family over the next 2 weeks and records the results in the graph below. So we've got a distribution of her actual shower times there. How do Suzanne's household results compare to a normal distribution model with a mean of 8 and a standard deviation of 2? So we need to discuss at least 2 of center, shape, and spread. So first of all, let's look at center. So theoretically, you know, for a normal distribution, hopefully you know that, well, our mean should be the same as the median, and it should be the same as the mode, right? So mean equals median equals mode for a normal distribution. I'm going to zoom in a bit. Okay, mean should equal the median, or it should equal the mode. But here, you know, we can see that this is definitely not, you know, super bell-shaped, right? So what that tells us is that, for example, you know, our mode, or, you know, our median number, you know, is probably around, you know, 8 or 7, or our mode is probably, you know, about 7. Our mean is definitely not going to be that. Because we've got all this skew, our mean is going to be some kind of untidy number, right? So we can clearly see that our mean is not going to equal the median, and it's not going to equal the mode, right? So we'll say for Suzanne's data, this is not the case. All right, this is not the case. All right, so that's fine for center. Let's talk about the shape. We'll say a normal distribution is bell-shaped. Right, a normal distribution is bell-shaped. That means data should be symmetrical, right? But if we take a look at Suzanne's data, you can see that, well, we've got this bell shape going on, but then it should theoretically stop here, but you know, it keeps on going, right? So what we do is we say, well, we've got the skew, and it's definitely skewed to the right. So we'll say Suzanne's data is skewed to the right. Okay, Suzanne's data is skewed to the right. Okay, therefore, this does not approximate, you know, the shape of a normal distribution well. Shape of a normal distribution well. Okay, and what else do we have? Well, we can also talk about spread. So let's look at the spread of our data. So, you know, hopefully, you know, for a normal distribution, we want all of our data or most of our data to be, to be contained within between 3 plus or minus 3 standard deviations. So, you know, this is my normal distribution here. This is our mean. Well, we should have that's, you know, we'll call about this being 1 standard deviation, negative, positive, 2 standard deviations, and then 3 standard deviations somewhere about here. Right, so it's not a very good graph, sorry, but all of our data should be contained within that. So let's first of all say that. So for a normal distribution, we want all, or we'll say almost all the data to be within, you know, 3 standard deviations of the mean or of mu, right? So for our theoretical, theoretical normal distribution model, if our mu is 8, then and our standard deviation is 2, so we've got 8 here. Then 1 standard deviation out should be 6 and 10. 2 standard deviations out should be 4 and 12. And then 3 standard deviations out should be, well, 2 and 14. Right, so this is our normal distribution, right? And this is all, in minutes. And this is our, mean here. 1 standard deviation out, 2 standard deviations out, 3 standard deviations out, right? But if we look at, the range, I guess, for this frequency data, we've got 0 and 20. So actually, all of our data is not contained within 3 standard deviations, which is not good. So let's say that Suzanne's data ranges from 0 to 20 minutes. Theoretically, 3 standard deviations should have a range of, and what did we say? We said 2 to 14 minutes, of 2 to 14 minutes. The data, I guess, is not fully contained within the, I guess, normal distribution range criteria, I suppose. So what are we trying to say overall? So ultimately we wanted to compare the normal distributions. We'll say, therefore, Suzanne's data does not closely approximate the normal distribution, right? Because it doesn't really tick all these boxes. Normal distribution. Okay. So, yeah, I apologize for the handwriting. It's not very neat, but that's all right. All right, part D. After 4 more weeks, Suzanne did another survey and found that the shower times in her household did approximate a normal distribution, and they had a mean time of 8 minutes and a standard deviation of 2. Suzanne considers only 15% of shower times to be acceptable. What is the longest shower time that Suzanne considers acceptable? So let's start these questions by drawing out a basic normal distribution, and here we know that the mean is 8. So mu is equal to 8, and we have a standard deviation of 2 minutes. Now, Suzanne considers only 15% of shower times to be acceptable. So we don't actually have a clear value of x, right? So if I remind you, we have this formula, z is equal to x minus mu over the standard deviation. So in this case, we know the probability 15% of shower times are acceptable. Okay, and because we're talking about shower times, obviously the lower the better in this case, right? Because we're talking about water shortages. So if we look at the z distribution for a quick second, sorry. Right, so just remember the z distribution is essentially the normal distribution with a very specific property. Mu is 0 and the standard deviation is 1. Okay, so just remember this is the z distribution where that the mu is 0 and standard deviation is 1. Okay, so here only 15% of the shower times are acceptable, right? So this area here should be 15% or 0.15. Okay, and essentially what we can do is we can use the inverse normal to get what we call the z-score. We can get the z-score here and then use that z-score to calculate the value of x, right? Which is what we want to do for this part here, right? So we know that we've got 0.15% or 15% of the area. We want to know what the value of x is, but how do we do that? Well, theoretically, we can actually use our calculator and do that directly, but I'll show you how to do that using the z-score. So remember, if we go to stat, distribution, normal, and this time we're going to use the inverse normal because we're not calculating a probability. We already have that probability and we want to find our value of x. Now our tail is to the left, our area is 0.15. Now because we're going to calculate the z-score first, our value of the standard deviation is 1 and our mean is 0. So if we do that, we're going to get a z-score of negative 1.0364. Then what we can do is plug this into that formula. Now, just to let you know, we don't actually have to do this. We can do it directly on a calculator by keeping the area to be 0.15 and just use the standard deviation, the mu that's already given to us. So if I put the standard deviation as 2 and mu is 8, it will give us a value of x, and that value of x is 5.927 minutes. Okay, so that's 5.927 is what will go there, but let me just finish calculating it with the z-score. So negative 1.0364 is equal to x, that's what we're trying to calculate, minus mu. Now our value of mu is 8 divided by 2, so we're going to use some algebra to rearrange this. So negative 1.0364 times 2 is equal to negative 2.0728 is equal to x minus 8. Therefore, x is equal to whatever that is, negative 2 plus 8. So x is equal to 5.9272 minutes, which is what we got there. Okay, and so that's the longest shower time, right? So that's our value there. Anything greater is going to be over that 15% threshold, so we're not going to accept it. Okay, sweet. So we'll just say that this is the longest shower time acceptable. Part E. Businesses use about a quarter of Auckland's water. Auckland Council states that about 85% of businesses use less than 2,000 litres of water per day. If the standard deviation for business water use is 450 litres, calculate the mean water usage for business customers, assuming that a normal distribution is the appropriate model. So, best step to do is to draw out our normal distribution. Now, we know that the mean is, we actually want to calculate the mean, so we don't know what the mean is. We know that the standard deviation is equal to 450 litres. They've also told us this here, about 85% of businesses use less than 2,000 litres of water per day, right? So we know that on here, we have 2,000 somewhere here, and then the rest of the area, will be 0.85. Okay, so because we want to calculate the mean, we're going to need to use our Z distribution formula. Z is equal to x minus mu over the standard deviation. Next, let's plug in the values that we know. So we don't know the Z score just yet, but we can calculate that. We will be able to use the value of x soon, but essentially the only thing we know for sure right now is that standard deviation of 450. So how do we go about calculating that Z score? Well, the first thing we need to do is let's just draw out our Z distribution. And our mean is 0, and we have a standard deviation of 1. So essentially, just look at this probability here. We know that we have a area of 0.85, okay, and we want to find the Z score for that. So, technically speaking, we have to put Z here, right, because that's actually what we're calculating, our Z score, right? So, all we're doing is we're translating this normal distribution down into a Z distribution, but because the, Z distribution is a normal distribution, all we're doing is we're taking that same area, or that probability of the area under that curve, that normal distribution, and we want to find the Z value for that. So how do we do that? Well, we're going to go to our calculator, click 2, for stat, distribution, normal, inverse normal, because we're calculating that Z score. Our tail is to the left, right? Because, why did I, shade it towards the left, not to the right? Well, we know 85% of businesses are using less than that 2,000 litres of water, but they're not using more. So if they were using more, then we would, put our area to the right, but they're using less, so we put the area to the left. Our area is 0.85, okay, and the standard deviation, because we're doing the Z distribution, needs to be 1 and the mean to be 0. So our value of Z is 1.0364, okay, and that's going to equal, well, now we can replace the value of x with 2,000, right, because this is specifically for 2,000 litres of water per day, right? So 2,000 minus the mu divided by 450, because that's our question specific values, right? 2,450. So all we do is we just rearrange for mu, or rearrange for our mean. So 1.0364 times 450, that gives us 466.38 is equal to 2,000 minus mu. If we subtract 2,000 from both sides, we're going to get negative 1533.62 is equal to negative mu. Therefore, we should divide by negative 1 on both sides. So therefore, mu is equal to 1533.62 litres. So that's our mean water usage. And that, if we plug that back up into our original diagram, that looks like it makes sense, right? So yeah, our mean should definitely be less than that 2,000, and it looks good. So I'm pretty happy with that. Let's go down to the next part. The council also stated a small number of businesses in Auckland, 1.5% specifically, use more than 15,000 litres per day. What issues does this raise for your answer to part I, and why? Okay, so let's just draw out our normal distributions again. So I'll draw out, okay, let's actually make it a bit bigger. Okay, and we know the value of the mean now. So the mean was 1533. Okay, and we have a standard deviation of 450. Okay. So the council is saying a small amount of businesses, 1.5%, are using more than 15,000 litres per day. Now, remember, our data needs to be contained within 3 standard deviations of that mean. So, if this is 1 standard deviation, this is 2 standard deviations, and this is 3 standard deviations. Let's actually calculate what those would be. So 1533 plus 450, that should give us 1983. If we add another 450, that's 2433. And then if we add, this is 1 standard deviation, this is 2 standard deviations, so our 3rd standard deviation or upper limit should be around 2883. Right, so virtually no data should be contained past 2,883 litres. But they're telling us that 1.5% are using 15,000, right? So, let's go ahead, just for example, right? Let's actually calculate the probability. The probability that X is greater than 15,000, right? If we put that into a calculator, we should get a probability that's very, very small. So NCD, because we're calculating a probability, we have no, our lower limit is 15,000 and our upper limit is 99999. Standard deviation 450 and 1533 is our mean. Look, it tells us that probability is 0. Our probability should be so small of that occurring because, our data should be contained within plus or minus 3 standard deviations. So what does that mean? Essentially, if we look at this data, so if we draw a new standard deviation, new normal distribution, and we know that 1.5% are using, more than 15,000. So, for example, assume that this is my 1.5% here, and 15,000, is my lower limit. What does that mean my mean must be? Well, first of all, assume that the mean is still 1533. Can I contain 15,000 within 3 standard deviations? I can do it if my standard deviation is super large, right? If my standard deviation is something like 5,000 or 4,000, then I will be able to contain that, within 3 standard deviations, right? So, another thing that we can do is, well, we can keep standard deviation the same, but if we just increase the value of our mean, that's going to allow us to get within 3 standard deviations, right? But what's the issue? The main issue here is we're saying, look, it's impossible for us to get 15,000 litres per day, within 1.5% of our area. So essentially, how can it be true? This is, it's a contradiction, right? In the sense, because they've told us that the mean, or the mean is 1,533. But here they're saying, well, also 1.5% are using more than 15,000. So either, the normal distribution does not, accurately model this, but yeah, that's our issue, is that, it's a contradiction for us to have a mean of 1,533 and to also have 1.5% of businesses using more than 50,000 litres. So that's our issue. So we'll say data, we'll say, litres of water must be within, we'll call this X, must be within plus or minus 3 standard deviations of the mean. Okay, this gives us a range of, this gives us an upper range at least of 2883, and you can calculate the lower range yourself if you'd like. 15,000 is way bigger or way greater than the upper limit. Therefore, it is almost impossible for there to be 1.5% of businesses using more than 15,000 litres. And we'll say, well, for this to occur, for this to happen, we either increase mu or the standard deviation, right? Let's look at question 2. Question 1 was quite long, so I hope this one is shorter. So Lawa conducted a survey and tested some New Zealand rivers and different land types to see if they were safe for swimming. The results from the survey are presented in this table. Part I, what is the probability that a randomly chosen river is an urban river and is unsafe for swimming? That is, we want the probability that we choose a river that's urban, and because they told us and, that means we look at the intersection, urban and unsafe for swimming. So urban and unsafe. So how do we find this, probability? Well, all we do is we look at our table. The first thing is urban. So we're looking at the probability that it's being urban and that it's unsafe. So just from this column, we need to look at that unsafe. We go down to get the urban, and then we look at each, row. We're looking for unsafe. This is our row, so we get to 57 there. All right. So the probability that it's urban and unsafe, well, we have 57 of those rivers, but we're looking, what's the denominator in this case? We're looking at a randomly chosen river. So that means all of our rivers. So that's going to be 810. So 57 divided by 810, it's going to give us 0.0704. And part 2, is a river in native vegetation more likely to be safe for swimming than a river in an exotic forest area? So we're going to have to calculate two probabilities here. The probability that given that we have a river in native vegetation, it's safe. So probability that given that we're in somewhere native, it's safe. Okay, and we also need to find the probability that given that we're exotic, we are safe. So all we'll do is we'll compare the two probabilities, and the one that's larger will be the more likely case. Okay. So what we do to calculate this, the probability that it's safe given that we're in a native, area. So we look at our, native column. Our native column is this column here. Okay. So, given that it's native, how many are safe? Well, we look across. Safe for swimming is 146. So 146 out of 194. Because remember, we only look at this column because that's the native column. Okay, so what's the probability there? Well, we just do the division. We should get 0.7526. Okay, and if we look at the probability for it being safe, given that it's exotic, we look at the exotic column, which is this one here. So we're just comparing it out of 26, and the ones that are safe are this column here, which is 15. Right, so 146 here, 15 here, but remember they have different denominators, 194 and 26. Okay, so 15 divided by 26 gives me 0.577. So which one was more likely? Well, the probability that we are safe given native is greater than the probability of it being safe if it is exotic. Okay, therefore, we'll say, the evidence is that we have native rivers are more likely to be safe than, exotic rivers. Now, the actual proportion of New Zealand rivers in each land type is different to those in that survey. So they've given us the actual proportions there. And what we need to do is we need to use table 1 and the proportions that are given to estimate the percentage of all New Zealand rivers that are unsafe for swimming. Okay. So essentially, what they're saying is if we look at the actual proportion of New Zealand rivers in each land type, for example, we've got 194, and that's out of 810 for native vegetation. 194 divided by 810, that's 23.95%. But they've told us it's actually 48%, right? So that means our survey's not quite correct there, but that's all right. All we need to do is use the table to calculate those proportions of unsafe rivers. what we're saying is, look, we want to find the probability that something is unsafe, or a river is unsafe. How do we do that? Well, all we need to do is find the probability, essentially that a river is unsafe and it's native. So unsafe and native. We also have to add that with the probability that it's unsafe and the next one, exotic. And we just add that with the probability that it's unsafe and pasture. And finally, the probability that it's unsafe and urban. Right, so this is an example of something that we call the partition theorem. Okay, so how do we calculate these probabilities here? Well, just so you know, the probability that we have A given B, so a conditional probability, is equal to the probability of A and B occurring divided by the probability of B. This is our kind of conditional probability rule. Okay, so we've got a intersection here, right? So we can rearrange this so the probability of A and B occurring is equal to the probability of A given B multiplied by the probability of B. So if we multiply by probability of B on both sides, we'll get that there. Right? So essentially, we know that in the table we have these conditional probabilities, right? For example, native vegetation unsafe if we have native vegetation. So if we multiply that by the actual probability of having native vegetation, we'll get this intersection, which is what we want. So if that doesn't make sense, that's fine. I'll go through it very slowly. So first of all, we want the probability that it's unsafe and native. So the probability that's unsafe and native is the same as the probability of it being unsafe given that it's native. So how do we find that? Unsafe given native. So we look at our native and we check if it's unsafe. So it's unsafe 48 out of 194, but we need to multiply that by the probability of it being native, which they've told us the actual probability is 48. Oh, sorry, 0.48, I should say. Okay, and what's that going to be equal? What's that going to be equal to? We can work it out. 48 divided by 194 multiplied by 0.48. That should give us a probability of 0.1188. All right, we have to do the rest of them. So we'll say that's for native. So what about for exotic? Well, exotic is going to be the same thing. So given that it's exotic, what's the probability that it's unsafe? So that's, we're looking at 20 out of 26 rivers. How many are unsafe? 11. So 11 out of 26 multiplied by the actual exotic, land area, which is 0.5 or 5%, which is 0.05. So what does that equal? Well, that's 11 over 26 multiplied by 0.05. We'll get 0.0211. Or 212, sorry. That's for exotic. What's the next probability? Well, we're going to do the same thing for pasture, so I'll go through it quickly. 424 divided by 528 multiplied by 0.46, because we've got 46 in pasture, that's 0.3694. That's for pasture. And I guess I just put the working here in brackets. We did 424 divided by 528. So 424 divided by 528 multiplied by 0.46. Okay. And the last one is urban. So 57 over 62 multiplied by 0.01. That's going to equal 57 over 62 times 0.01. That is a very small probability, which is 0.00919. So all we do is we sum these. Therefore, the probability of it being unsafe is equal to the summation of, let's call these little x, for example, right? So all I'm saying is I'm just going to add these all up, right? So 0.1188 added with 0.0212 added with 0.3694 added with 0.00919, we have a probability of 0.51859. We want the percentage, so we just multiply that by 100 times 100. We'll get 51.859%. Okay. Part IV, how confident do you feel that this probability would be correct for all New Zealanders. Now, I think I said at at the beginning that, okay, this is for each land type from the survey, right? So, this is different from those in the survey, right? So, as a result, if we look at native vegetation, 194 over 810 is like half of 48%, right? So, I would essentially say I am not confident that this is correct. What's the reason? Well, for example, when we calculate, probabilities, we want our, survey, I guess we'll say land area does not represent the entire population. Okay, so what do I mean by that? For example, let's look at exotic, right? So exotic is probably a good example. So probability that we have an exotic river is equal to 26 divided by 810. 0.032. That's from our survey. Now, we're told that the actual percentage is 5%, right? So this is 3.2%, but reality, is that it's 5%, right? So because our land area, so it'll be quite off for the rest of them. Our land area is not matching. Our land area from survey is not matching. The actual data. It is hard for us to generalize. Okay. Is there something else? Well, this paper is from 2022, but if we look at our data, it's from 2020. So we'll say plus older data may not represent today. 2020 versus 2022. Okay. Oh, you're still going. Okay. Part B. Mia and Joe want to go on holiday near a swimmable river. They find the summary table of popular river sites in the North and South Island. Then they are monitored to check if they're swimmable. So we've got a table here. What is the probability that a river chosen at random from these monitored sites is safe for swimming? So probability that a river is safe. So all we do is we sum, the safe rivers, and we divide that by the total amount of rivers. Right, so what's the probability that they're safe for swimming? Well, we just sum those ones from both the North and the South Island, 170. And we need to divide that by all rivers, right? So safe or unsafe, we need to sum them together. So 105 plus 65 plus 74 plus 34, that's divided by 278. So 170 divided by 278 is 0.6115. Part 2, Mia looks at the data and says it's more than twice as likely for a river in the North Island to be unsafe for swimming compared to a South Island river. But Joe says, well, it's actually only 20% more likely for that to happen. So we need to explain each person's reasoning and decide if either reasoning is supported mathematically. Okay, so we've got two claims here. So we'll start with Mia's claim. What's Mia's claim? Mia's claim that is more than twice as likely for a river in the North Island to be unsafe compared to a river from the South Island. So, look, what we're saying is that the probability that given we are in the North Island, that it is unsafe. So that probability is going to be more than twice as likely for a river in the North Island to be unsafe. So this is twice as likely compared to the probability from somewhere in the South Island. So this is the probability that it's unsafe, given that we're in the South Island. Now, what can we do here? We can rearrange this and find a relative risk. That is the probability that we're unsafe, given that we're in the North Island, divided by the probability that we're unsafe, given we're in the South Island, should be double, right, or 2. Now, what's Joe's claim? Joe's claim is that it's only 20% more likely for a North Island river to be unsafe compared to a South Island river. So we're doing a legit the same thing, probability that we're unsafe, given that we're in the North Island, divided by the probability that we're unsafe, given we're in the South Island. So we're looking at relative risk here, but he reckons it's only 1.2. So what we do is we'll actually calculate this. So we can use our table. So we'll say now, the probability that we're unsafe, given that we're in the North Island, is equal to, so given that we're in the North Island, what's the probability that we're unsafe? So what's the total? 74 plus 105, 179. Okay, so let's just draw in our totals to make things a little bit easier for us. 74 plus 34 is 108. 65 plus 34 is 99. And then our total is 179 plus 99 is 278. Okay. So going back to our question, probability that given we're in the North Island, so out of 179, what's the probability that we're unsafe? It's 74. 74 divided by 179 should give me 74 divided by 179, that's 0.4134. Okay, and the probability that we're unsafe in the South Island is, so out of 99 rivers, it's 34 are unsafe, so 34 over 99 is what? 34 over 99, that's 0.3434. Therefore, the relative risk is equal to, well, the probability of being unsafe given that we're in the North Island, 0.4134, divided by the probability that we're unsafe in the South Island, 0.3434. So we do the division, 0.4134 divided by 0.3434, we get 1.204. So that means Joe's claim was 1.2, but Mia's claim was 2. So Mia's she's just completely wrong there, right? So therefore, Joe's claim is correct. Mia is wrong. So Mia needs to go back to school. Is that all we need to do? Explain each person's reasoning. So why would Mia say that it's twice? So Mia reckons it's more than twice as likely. So let's compare these just two numbers straight away. 74 divided by 34 is 2.176. So that's probably what she's looking at. So we'll say, look, Mia was comparing the raw numbers of unsafe North Island, so unsafe North Island and South Island rivers, unsafe North Island and South Island rivers. She did not consider that we need to compare proportions. So why do we need to consider proportions? Well, that's because our totals are completely different, right? So because our totals are completely different, that can sometimes skew, or not sometimes, definitely skews the way that we understand our proportions or probabilities, right? So we always compare probabilities and not raw values. Okay. All right, question 3. A large online survey was carried out asking 2,500 New Zealanders for their views about water use. Okay, we've got all of the percentages there, and we want to fill out this probability tree. So 87% were concerned about water shortages. So 0.87 were concerned. Now remember, our probabilities must sum to 1, so that means that the not concerned must be 1 minus 0.87, which is 0.13. So now, given that they're concerned, so we look down to our next branch, they've already filled it out for us, so we don't need to worry about that. So we'll just look at the ones that are not concerned. So of those that aren't concerned, half of them usually try to save water. So usually save only. So sorry, that one's restrictions. So they only save when there's restrictions, and then there's some that don't. So never. Right. So I'm just copying these here, but I just shortened it a little bit. So half of them usually try to save. So that's 0.5. A quarter of them only do it when there's restrictions, and the rest never. So 0.5 plus 0.25 is 0.75, and to get that last one, remember our probability must sum, down the branches must sum to 1, so 1 minus 0.75 gives us 0.25, right? So, a quarter of those that aren't concerned about water shortages never try to save. Greedy people, eh? Part 1, pi. What is the probability that a respondent chosen at random is concerned about water shortages and usually tries to save water? So we've got the AND keyword there, so we're going to do an intersection, or so probability that we are concerned and we save usually. So all we do is we go down our branches, so probability of being concerned is 0.87, right? And we just multiply that, so we always multiply when we go across the branches, that they try to save is 0.8. So we just multiply 0.87 by 0.8. Okay. And that gives us a probability of 0.696. Part 2, of 2,500 respondents, how many say we only save water when restrictions are in place? So what's the probability that we save, when there are restrictions? So probability that we save when we have restrictions. So note that this is, not an intersection. We actually only care about this here and this here. So how do we work that out? What we have to do is we have to go across each branch and calculate, that probability for each, time that we see that restricted, and then we add them together, right? Because we don't. We add them together because we want to find that total probability, right? So how do we do that? Well, what's the probability that we save when we have, water restrictions and we're concerned? So, we can break this down. Probability that we, concerned and we only save when we have restrictions. And we sum that with the probability that we're not concerned, we don't care, and we only save when there's restrictions. Right, so this is an example of the partition theorem. If we sum those together, we'll get the total probability that we only save when we have water restrictions. So what's that going to be equal to? Well, we just multiply across the branches, so 0.87 multiplied by 0.018, 0.1566 added with the probability of not being concerned, which is 0.13, multiplied by 0.25, which is 0.0325, and that's because we're looking at that restrictions there. So if we sum those together, we're going to get a probability of 0.1891. But we want to know of how many people. So 25 out of 2,500 people, so we need to multiply that probability by 2,500. We'll get 472.75 participants, but we can't have 0.75 of a person, so let's round that down to 472 respondents. All right. Part B, a secondary school teacher wondered if young people's views would be similar to those, compared to that first survey. So she surveyed 200 students from year 9 to 13 at 2 high schools. And she found 70% of students were concerned if they were, okay, so we've got all those probabilities there, and we want to draw a tree. So, okay, we're either concerned about climate change, so concerned about climate change, or we're not concerned about climate change. All right. Then if we were concerned about climate change, some of them were concerned about water shortages, and then some of them weren't concerned about water shortages. So all we do is we'll say, look, they were concerned about water shortages, or they weren't not concerned about water shortages. So concerned about water shortages or not concerned about water shortages. Okay, so just think of it like this. Our first section is about climate change. So level 1 is about climate change. And our second level is about water shortages. All right. So now we can go ahead and put our probabilities in. So 70% cared about climate change. And that means that 30% didn't, right? Because 1 minus 0.7 is 0.3. If they were concerned about climate change, 85% were also concerned about water shortages. So that's 0.85. That means that the complement, or 1 minus 0.85, gives us 0.15. Then look at our third bullet point. 55% of those who were not concerned, so we're looking down this branch here, were concerned about water shortages. So even though they don't care about climate change, they do care about water shortages. So then we just do 1 minus 0.55 to get that other branch, which is 0.45. So if you do this in your own time, just check that every single branch sums to 1. If it does, that means you're on the right track. So that's my probability tree. Okay. And we also need to calculate a probability that a student chosen at random is concerned about water shortages. So the probability that a random student cares about water shortages. So they're concerned about water shortages. So how do we do that? Well, we need to calculate all branches where we care about water shortages. So that's this branch here and this branch here. So how do we do that? Well, we need to multiply across our branches, remember, so 0.7. So I'll write it out, sorry, so you get a better idea. So this is the probability that the probability that we care about climate change and we care about water shortages summed with the probability that we don't care about climate change, but we do care about water shortages. Right, so that's our partition theorem at work again. So how do we calculate that? Well, we just multiply across the branches and sum them together. So 0.7 times 0.85 is 0.595. And all we'll do is we'll sum that with 0.3 and 0.55. 0.165. Okay, so if we sum those together, we'll get 0.76. The teacher also found that the probability that a student saved water was 2 times greater if they were concerned about water shortages than if they were not concerned. The probability that a student saved water was the same whether they were concerned about climate change or not, and that the overall probability that a student in the survey saved water was 0.5632. So we want to find the probability that a student is not concerned about climate change, is not concerned about water shortages, and does not try to save water. So we're adding a new level to our tree. So what I'll do is I will duplicate this and bring it down so we can have a better look at what we're actually doing. So we're adding a new level to our tree. So whatever is happening, right, they either try to save water. Okay, yeah, let's do it in pencil. So they either try to save water, so save, or no save, right? So they either try to save water or they don't try to save water. Right, so they either try to save water or no save. So every single outcome will either try to save or no save. And save or no save. So that's our third level now, right? So our first level is about caring about climate change, our second level is about water shortages, and our third level is about saving, if you actually save water or if you don't actually save water. So what's our probabilities now? So the probability that a student saved water was 2 times greater if they were concerned about water shortages than if they were not concerned about water shortages. So if you're concerned, let's probably do the student saved water was 2 times greater if they were concerned about water shortages. Okay, so essentially we care about water shortages, right? So where do we care about water shortages? We care about it in these 2 branches. So if we actually did care about water shortages, then that's going to be 2 times greater. It's going to be 2 times more likely for us to save that water, compared to if we, weren't concerned. Okay, so not concerned are these ones. So what we're saying, if we care about water shortages, we don't know what that saving probability is, okay? But we know that it's double as likely, so 2x, right? So we'll say, let x be the probability of saving water. All right, so we can use x. Actually, I don't like x. Let's use a. So let a be the probability of saving water. Okay, so 2a. So if we care about water shortages, we're always going to be double that. If we are not concerned. So we're not concerned about water shortages, so we'll put a on these branches because they don't care. So if we care about it, it's double whatever the value of a is. So actually, a is not the probability of saving water, but a is the probability of saving water if we don't care about water shortages. Okay, so that was not very well explained, so let me try to explain it again. So 2 times greater if we're concerned about water shortages than if we're not concerned, right? So if a is the probability of us, saving water and we don't care about water shortages, then it's going to be twice that probability if we are concerned about water shortages, right? So we look down the branches. If we care, it's 2a. If we don't care, it's a for saving only, okay? That brings up a new question. What are the probabilities of us for, caring for water and not saving? Well, it's going to be, remember that our probabilities must sum to 1. So the sum, down our branches, so the sum of all probabilities must be 1. So therefore, this is going to be 1 minus 2a. This is going to be 1 minus a, 1 minus 2a, 1 minus a. All right? Anyway, let's get back to the problem at hand. So what's the next part? The probability that a student saved water was the same whether they were concerned about climate change or not. Probability that a student saved water was the same whether they were concerned about climate change or not. Okay. The overall probability the students save water was 0.5632, right? So the probability that we save water is equal to 0.5632. So one probability, what we're actually trying to calculate, is the probability the student is not concerned about climate change. It's a probability that we are not concerned with climate change, and we're not concerned about water shortages, and we do not try to save water. So if we go down our branch, we're not concerned about climate change, we don't care about water saving, we don't care about water shortages, and we don't try to save any water. So how do we calculate this? Well, this is the same as the probability of 0.3 multiplied by 0.45 multiplied by 1 minus a. So if we want to work this out, this is going to be the same as 0.3 times 0.45, which is 0.135 multiplied by 1 minus a. So we need to now work out the value of a. And remember, a is the probability of us saving water if we don't care about water shortages. Okay, so essentially, we know that the probability of saving water as a whole is 0.5632. So the probability of saving water is equal to the probability of essentially saving water, saving water, and essentially we have to go through every single branch, look for the ones that we are saving water. Okay, so we need to look at this branch. Sorry, I highlighted a different color. This branch, this branch, this branch, and this branch. Okay, that's all about saving water. All right, so that's going to be fun to calculate. So the first one's going to be 0.7 times 0.85 times 2a. Okay, 0.7 times 0.85 times 2 is 1.19a. Added with 0.7 times 0.15 times a, so 0.7 times 0.15, that's 0.105a. Added with, let's go down to the not caring about climate change, 0.3 times 0.55 times 2a is 0.33a. Added with the last branch, so 0.3 times 0.45 times a, because we only care about saving branches. Okay, that's 0.135a. So if we sum that, that'll give us the total amount of water saved. 1.19 plus 0.105 plus 0.33 plus 0.135, 1.76a. Now, we know the probability of saving water was 0.5632. That's equal to 1.76a. 0.5632 divided by 1.76 gives us the value of a, which is 0.32. That's our probability if we save water, if we don't care about water shortages. So, this probability, remember that we just needed to work out the value of a. So if we go back down, this is equal to 0.135 times 1 minus 0.32, because we just substitute in the value of a. 0.135 multiplied by 1 minus 0.32 is a probability of 0.0918. Crikey, that was a bit of work, but yeah, that's how we calculate that probability. Part 3. The teacher uses the findings of both surveys to claim that New Zealand students are about 25% less likely to save water in their homes than the general population. Discuss the validity of that claim. Okay. So we have a relative risk here. The probability that we are a high school student. So the probability that given that we are a high school student, we are going to save water divided by the probability that, given that we are, given that we are part of the general population, we're going to essentially, probability that, given that we're in the general population, we're going to save water. So if we do a relative risk here, if it's 25% less likely, we should be getting a probability essentially, less than 1, or a probability of 0.75. Okay, so let's actually do the calculation. So the probability that given that we are in high school, so where is our high school? Given that we're in high school, we're going to save water. So is it here? Yep. So this is our kind of high school survey. So 0.5632, and divide that by, given that we are part of the general public, what's the probability that we saved? So we need to go all the way back up. So this is our general survey. So given that we're in the general public, what's the probability that we did save water? I think we calculated it. Maybe we didn't calculate it. So the probability that we are part of the general public and we did save, we're going to calculate both of these branches here. 0.87 times 0.8 added with 0.13 times 0.5. So that gives us 0.761. Okay, and if you were doing this properly, you need to write out your working. So if we do that calculation, we should get 0.74. So this is very close to 0.75, right? So we'll say after calculating the relative risk, the relative risk is very close to our theoretical statement, right? So they told us 25% less likely. That's the same as 1 minus 0.25, which is 0.75, right? Because when we do relative risk, we expect a decimal. If it's less than 1, that means it's less likely. If it's more than 1, that means it's more likely. So I hope that makes sense. Yeah, so it's very close. So therefore, the claim on the surface is valid. But, we need to look, I guess, more into, can we actually make, these generalizations? Well, to be honest, so we probably cannot make these, generalizations. What's the reason for that? Well, we need to actually look at how we've done our surveying. So, first of all, if we remember, a high school survey was only surveyed 200 people from 2 high schools. So, our high school survey is only from 2 schools. And for generalization, we want a wide range of data. So for example, if I, just interview 2 schools from 2 high decile schools, that's not going to be representative of schools, if those 2 decile schools were in Auckland, that doesn't represent schools that are in Kaitaia, for example, that, might not be super high decile, or, comparing different schools, we need a wide range of data, right? So that's something that we can't just, simply make that generalization. Is there anything else, right? If we look at our original data, we did a large, large is good. Okay, so we can say, if we were discussing validity, okay, they did a large survey, that's good because we're going to get more of the population, so it's going to be closer to our population values. However, the survey was online. Okay, so general survey was online. Now, if you think about this, if we do an online survey, you're going to get a very, very specific demographic of people, right? For example, if we consider more elderly people, bless their souls, but they're not very technically gifted. Some of them aren't very technically gifted, right? So you're not going to get, representations from them. You also might not get representations, from, a little bit more, I guess, younger people that might not, or, people that, are in poverty and they might not be able to afford their own devices. So you're going to get a very, very specific demographic of people. So this will give us a specific demographic of people. So because of that, biased results. Right? And that's it. So I hope you enjoyed this video. Sorry for the messy handwriting, it's been a while. But yeah, good luck for your exams. Cheers.